In this example, I'd like to use different constraint types and throughout the example, figure out how to use those effectively in different ways to produce more controllable results. So looking at this scene, we have a very simple collection of bricks here. So I'm going to copy that over so we can work with it. We've got some ground, pretty simple there. And here I've just made a little contraption for a wrecking ball. So everything in dark gray, just go ahead and copy over. And we're going to try to set up the rest of the simulation with constraints. Okay, so let's start off with the wrecking ball. So let's build a new DOPS network. I'll put this in number 3 input. And let's make a packed object. Third context geometry. Okay, that came in. It's really just an object here set to inactive and an object here set to active. All right, so let's set that up with some gravity and a rigid body solver. Might as well go ahead and make our ground plane. Actually, the ground's already in the example. Okay, and it just falls. So we need to constrain this active object to this inactive object. So throughout this example, I'm going to label the constraints based not on what type they are, but what they're actually doing. So let's, similar to the last example, let's actually just make a one standard constraint here. So I'm going to go ahead and use an add, and let's delete the polygons or primitives. So we have 2 packed fragments. I'm just going to delete those. And now we're left with 2 points with a name attribute. And you can make that like this in order to view it in the scene. Okay. There we go. We have ball attach and ball. And now let's go ahead and make a polygon by group. So we have a polygon connector. And with this constraint name, let's call this something representative like wrecking. Constraint underscore name, primitive string wrecking for the wrecking ball constraint. Okay. And because we probably are going to want some more constraints, I'm going to follow that up with a merge, and then I'll plug that into the second input. Okay, so we want to make a new constraint network. And let's try out the new bullet soft constraint relationship. This is similar to the spring constraint, but it's designed specifically to be more artist friendly to work with. It's a lot more stable, and it simply has a stiffness parameter. So plugging that in, I'm going to set the name to wrecking, and then we want to read from the second input. And if that showed up, then it's successful. It's going to snap right back, and that's because we haven't yet assigned the rest length. We need to override this parameter. So back up to the top here, I'm going to do a measure sop. Okay, so we want to measure perimeter, rest length, and now this should get overridden. And if we want it to be a little more stiff, increase that, and it should hold its shape a little better. There we go. So that's working nicely. Okay. Also, this object under physical, I'm going to make this around 8,000, which would be more like steel. Okay. And notice the soft constraint isn't going to be affected by the new weight. Now let's set up a more elaborate constraint network. So here we have a bunch of bricks, and we have the ground. And right now there's no name attribute, so I just want to go through the process of setting that up. So I'm going to use a digital asset I made, destruction, attribute, and name, just to assign a name by connectivity. So here we have chunk, etc., etc. I want to change that to brick. Okay, so now we have brick 83, brick 82, and let's get a representative color. Maybe a little less color variation. Okay. So that's fine. And now here's the ground. We only have really one piece of geometry here. So I'm just going to simply assign the name attribute directly. Name, primitive, string, ground. There we go. And I'm going to do the assemble node on both of those. Okay, so we do not want to create a new name attribute, and we want to create pack geometry. So now the name is represented on each point instead. Same with the ground. And I wanted them to be packed at this stage just so we can set active and inactive. So these are obviously going to be active. They're going to move around and break. And this is not going to be active or affected by gravity. So I'm going to do an attribute create again. Active. Point integer. And I'm just going to set this to op digits. And that'll pull the integer off of the name itself using the dot to reference the current node. Okay, so I'm going to do active 0 for the ground and active 1 for the bricks. And that should be set up and ready to go. Okay, I'm going to merge those together. And let's put that into the first input. And let's follow that up with an RBD packed object, first context, and merging that together. Okay, and we have a destruction simulation. A few problems though. For one, there's some settling behavior, and next they seem to break without incident. There's no resistance whatsoever, and brick is randomly falling off here. I'm actually surprised that the wall held up as well as it did. Okay, let's set this more like to the density of a brick. So under physical, once again, I'm just gonna up that density just a little bit. That's about all. Okay. All right, so what can we do here? Well, to start off, I just want to make an initial set of constraints of glue constraints, and the glue constraint is going to meet a certain impact threshold before it breaks. Okay, so let's name this wrecking, and the data name will be OS. Okay, just for cleanliness. And now let's make a glue constraint relationship. Also OS, and this will be called init. Okay, so the init is just going to keep it in the same spot with a very, very light constraint. All right, so I'm just going to merge these two together. Okay, and let's set up a glue constraint network here. So I mentioned in a previous example that you might want to use tools, make your own tools, use studio tools to set up more elaborate networks of constraints. And here, what these would need is they would need a constraint, say it's this brick, you need it to this, which is touching, and to that, which is touching. So I've made a digital asset to do that, the make connected constraints, and it's really just making lines just like we did when we set up the constraint from scratch. It's supposed to operate on unpacked geometry, so I'm just going to unpack that first. There we go. Okay, so it's made constraints between, say, this brick and then its nearest neighbors. And if we wanted to actually measure the distance between these, I would just say 2 centroids. And now we have a pretty representative constraint network to work with. I have it defaulting to the name of glue so that we don't have to set that up again. But instead, I'm going to call this init. Okay. And notice it's also connected to the ground. There's tools in the default side effects operators in order to do similar things like the connect adjacent pieces. But here I'm just going to use this since it has a few more features. Okay, and I'm just going to merge this guy with the constraints. Okay, so now we have a bunch of constraints that have the name, the constraint name attribute of init, and one that has wrecking. Okay, so now let's see what happens. Looks like it detected that. And to test this out, I'm always just going to set this to -1 just to make sure everything is working. And you see now it's not budging at all. It's respecting an infinite strength there. Okay, but I want this to be a very, very weak strength. So as long as we don't have any settling behavior, we're okay. So I'm going to try a strength of 1. There we go. So it just happened right as it just broke right as the wrecking ball came through. It didn't have any pre-settling behavior. I personally think that glue is probably the fastest and most stable way to arc direct and control a rigid body simulation. And if you base most of your simulation off of glue, then you can focus the really fancy effects, bending, twisting, on more of the soft and adaptive constraints, such as the bullet soft constraint. So I'm going to make another glue constraint. This one is purely just for the initial break, and subsequent constraints, I might want to add exactly the right amount of force. So let's test to see what the right amount of force to break this apart is. All right, so I'm going to try to up this and keep upping it until we really kind of see the difference. Okay, well, this is init 1. I'm going to change that to init temporarily. Okay. Okay, really want to see the difference in how this thing responds. I'm going to find that sweet spot. Okay, so that's responding a little too harshly, and a strength of 10 was a little too weak. See, you've got, it kind of gets touched and then the whole thing crumbles. So we need to find that difference. Looking pretty good there. We see we are starting to have some variation. Breaks first. Okay. Let's try to up it just a little more. Yeah, I think that's good. Okay, that seems like what a wrecking ball would do. All right, so I'm going to call this guy glue instead. Okay, so right now it's just using wrecking and init, and make sure to change that back to OS. And we might want to switch later and experiment with this glue constraint. Okay. So the whole thing about breaking something is there's usually some resistance that you can't really describe. This resistance is going to be a product of friction from all the concrete and the plaster in between these bricks. It's going to be forces propagating through almost infinite number of molecules, and we just can't reproduce that in the computer. So we have to kind of make up the inherent bend of a simulation like this with constraints. And that's probably the most straightforward way to do that, if not soft bodies. So using constraints for that, let's make an identical network from this, but let's make it also have soft constraints. Okay, so I'm just going to use an attribute create here. Constraint name, primitive string, and let's call this soft. Okay, so we've just overwrote that attribute, and I'm going to merge these together. So we have the init and the soft, and those are going to operate at the same time. All right, so I'm going to make another bullet soft constraint. We'll call this soft. And let's put that in here as well. There we go. Pretty cool. Not really what bricks do, but I think it's amazing. Previously to bullet constraints, this was incredibly difficult to do and very slow. And here it's pretty much faster than real time. All right, so let's find a nice little sweet spot in the stiffness. And I think a soft constraint would be great for representing the first few frames of the impact like this. So let's try 10. And this is way too soft. I don't envision bricks would kind of distort like that and maintain their integrity. I think something like 500 might be a little too rigid. I can probably get the same result with a glue constraint and some simple collisions. So I think the number I ended up on the previous example and the pre-made example here is around 100. And I think that's a pretty good shockwave impact looking effect. So this next operation is going to mimic what was a two-state constraint. And we need to mimic that in Bullet. And this might be a little bit advanced for this stage. So if nothing else, just gather the fact that we can use the constraint name to switch between and use multiple constraint types in unison. So here, let's take that to the next level just a little bit. All right, so what we want to do is if the wrecking ball hits, I want to use the first few frames, maybe 2 or 3 frames of this. And if the force is dramatic enough, I want it to break the constraint, which a soft constraint can't break. And if it's not, then I want it to turn into a glue constraint and hold where its current position. All right, so how do we pull that off? Well, we're going to have to use a solver. Here's a SOP solver, and the constraint network has a solver input into it. Now, working with this, we have to make sure that we're not directly in here because it won't really cook the outside. It won't cook .NET 1. And we can't work here because then we can't see what we're doing. So here's a little trick, is to do 2 views, and that will force things to cook. So I'm going to dive into the SOP solver and hit the pin. And going back out, I'm going to hit the pin here. And so everything we do in here will be forced to cook, and then we can see this happening, and we'll be able to work in here. Okay, I'm also going to say use external SOP, and I'm going to make a null and call that output. So whatever we plug in here, specifically the relationship geometry, which is the constraints, we're going to say always cook this, not where the visibility flag is. Okay, and that's really a great way to work. All right, so diving in, what's going on with these constraints under the hood? So here we've got force that's being applied to this soft constraint, and we have impacts that are being applied to the glue constraints or the init constraint. Okay, well, I'm interested in the soft constraints. I want to say if your force is greater than a certain amount, then count the frames. Working in a SOP solver basically allows us to treat geometry like a particle sim as far as attributes. We have a natural feedback loop that happens, and once it gets hit, I want a timer to go off to where I can count 3 frames if 3 frames have passed once the soft constraint got hit, because I don't want this brick wall to be too bendy forever. So I'm going to drop down a primitive up, and we can do our logic in here. And I'm only going to be applying this if the constraint name is soft. We don't really need to do this to the other types of constraints. So at constraint name equals soft. Okay, so let's get the force off of the geometry. So current primitive number, first input, float, primitive force. And I'm going to test that. Compare. And let's see if it's greater than whatever we deem necessary to set off this timer. So test force. And here I'll just put this in the color, and just so we can see that happening, let's attribute promote. Okay, and now we should see, okay, so that's kind of working. Now eventually that's going to go back to 0, and I really just want to do a test and then activate an attribute to be a timer. So we can say if this is true, parameter, we can call it soft timer, integer, export when input is connected, use this node. Okay, so this is going to be our export. So if this is true, export it. And here I've created a feedback loop, just like in particle. So it's reading in and reading out. Okay, so if this is true, then add 1 to this. Now notice it sets some of these to 1 if it was a constraint name of soft, but it's staying there. So to really have a feedback present here, we have to connect this to the output, and then it's writing out, and on the next frame, reading in. So now soft is always just counting. Okay, so we only want it to start counting once it gets hit. So there we're going to say, okay, add 1 to it, but only if this is true. So we can use a two-way switch. In comes our condition that it got hit. And if it's true, then add 1 to that. And if it's false, then just use the previous value. And now it gets activated once it gets hit. Next, I want these to be able to break, and they should break if at any point the soft timer has been activated and it's greater than a certain force threshold. So I'm going to use another primitive up here. I'm just going to copy and paste that, and this time it's only going to operate on at soft timer is greater than 0. Okay. And let's see, so we don't need anything concerning the soft timer in here directly. We do want the force though. So we're going to test to see if a force is greater than a certain amount. And if it is, we're just going to remove the constraint because these are just lines. That's one of the really beautiful things about using procedural geometry to create and manipulate simulations. So I'm going to do a two-way switch from the current primitive number. If it's true, it should go in the first input, or -1, which does not exist. It's not a primitive number, and we'll do a remove prim. Okay, so now if it's greater than 0, they will just disappear and break. Not really what we want. So let's set a different force threshold, and we should be able to test that and see. So let's take a look at some of these force values on the soft constraints. And these force values are looking to be pretty high here. So we're going to need to test for something a bit larger. Okay, so here it's just breaking a few. And that's kind of nice. That's actually more of the effect we're going for, because we want the really difficult breaks, the really forceful breaks to detach, but the rest should just bend for a few frames. So let's set that down a little bit, maybe 700. There we go. So what we've essentially done here is we've just mimicked the old two-state constraint, and what that did is it just switched between one constraint type and another constraint type, and what you'd use for a scenario like this is a no constraint relationship. Well, in Bullet, it's just, if it's gone, it's a no constraint relationship, and if it's there, it has a constraint relationship. Well, I want to just do a little test now because I don't want to have this keep wiggling around and settling. It really shouldn't be curved like that for more than a frame or two as the internal forces give way. So I'm going to do a new primitive wrangle, and let's just set it to glue if it's older than 2 frames. So for the group to operate on, we'll do soft timer at soft timer is greater than, let's say, 2 frames. And then we'll just set this to the glue name. So string at constraint name equals quotes and semicolon glue. All right, so let's see if that works. So after 2 frames, yeah, we're getting a really nice, we get the best of both worlds. So we got this bendy stuff at the impact, they're breaking, and they're also deforming a little bit and holding their position. They can still be hit again and it would break because it's just a glue constraint. All right, so I hope from this example, we're able to really find some ease with constraint networks and constraint types.